Hello and welcome to the presentation of our work, Real-Time Event Simulation with Frame-Based Cameras. I will start with a quick introduction how an event camera works. We will see on the top the output of a standard camera and on the bottom the output of an event camera. With the standard camera we have at the fixed frame rate the frames, and with the event camera we have the positive and negative events with black and red, which report intensity change. So if there is no intensity change in the scene, we don't get data, whereas with the standard camera, we do get redundant information. If the disk is spinning very fast, we tend to have motion blur with a standard camera, whereas we have less of a problem with the event camera. So these two sensor modalities are very different. Event cameras have the advantage of a high update rate and of 1 megahertz, which results in a temporal resolution of microseconds. They have a high dynamic range, almost no motion blur, and low power consumption. However, they do not give absolute intensity, but pixel-wise intensity changes. Because the data format is very different, standard computer vision algorithms can't be applied straightforward. And since the technology is relatively new, it's not as mature as standard cameras. Now, why do we want to simulate event cameras? Similar to normal cameras, it is faster to get simulated data for learning-based tasks. And because event cameras are relatively new sensors, they're quite expensive and scarce. This makes event cameras inaccessible to the majority. In the literature, there are already multiple event simulators. Most of them do focus on a realistic camera model, and these are successfully used in learning-based applications. However, they do not run in real time, which could be important for robotic applications. For our method, we have the following setup. We have a camera which provides us frames, and we want either an event stream or accumulated event frames, and we want that this event simulator can run in real time. A first approach, which is similar to previous methods, takes 2 consecutive frames as input. We then use optical flow for interpolation. With subtraction and thresholding, we get either the event tuples, X, Y, timestamp, and polarity, or accumulated event. For interpolation, we either can use dense or sparse, and depending on the scenes, this can lower the runtime. One major contribution of this work is the difference frame interpolation, where we have 3 consecutive input frames. By subtraction, we get 2 consecutive difference frames, and by interpolation, we get an interpolated difference frame. So we only interpolate the difference frames, which further improves the runtime. We use 2 different datasets to evaluate our event simulation methods. One is DSEC, where a camera runs at 20 frames per second. Here we use the dense interpolation approach with Farneback optical flow. On the top left, we see the output of the frame camera, which we use as input for the event simulator. On the top right, we see real accumulated events from the dataset from a real event camera. On the bottom left, we see one of our event simulation methods, and then V2E and VIT2E, 2 state-of-the-art event simulators as a comparison. A second dataset is a table tennis ball sequence where a camera runs at 150 frames per second. It's recorded in our table tennis robot lab, and it uses the difference interpolation approach. As I mentioned, real-time runtimes are very crucial for us. On the left-hand side, we see the run times and for the car dataset, and on the right side for the table tennis dataset. Both are in milliseconds, and the y-axis is in log scale. The blue bar indicates 30 milliseconds, which we consider as real time. Here on the right side in green are the state-of-the-art methods, and on the left hand on both plots are our methods. Also, not all of our methods actually run below 30 milliseconds. They're still faster than the state-of-the-art by several order of magnitude. In this example, we show you a ROS setup where we have a ROS node that streams frames from a normal webcam from a laptop, and on the right-hand side, the output of our event simulator, which shows that this method runs on a normal laptop without GPU. So as a conclusion, we showed that optical flow-based event simulation methods are capable running in real time. We presented a novel event simulation method which leverages the sparsity of events in the interpolation to further improve the runtime. And in the paper, we provide a qualitative and quantitative results comparing our event simulation methods with existing ones and real event cameras, and the guideline when to use which simulator. With this, I thank you very much for your attention. Please check our project page for the source code and further information. Bye.